I'm going to summarize what I discussed a little bit and what Somen was trying to explain to you. Okay? So we are talking about our linear problem, and so what's happening now? Okay, so what we have here is our data D, our model M, and our forward model is D equals GM, right? And what we basically showed you is that M estimated is GT, GT on D. Okay? So, what is G? Right? So, let's say that I have observations y1, y2, y3, let's say y4. I have 4 observation points. Or just 3, for example. So here I can say my y is a plus b x1, right? And this one is going to be a plus b x2, and this is going to be a plus b x3. Then y4 is going to be, no, it's not letting me write. Okay. So here I can write this as a column vector y1, y2, y3. This is equal to, then on this side I can write a and b, and then in the matrix I have 1 x1, 1 x2, 1 x3. Is this clear? So that's your G matrix. Okay? So then you transpose this, multiply with G, take its inverse, multiply with GT, that, and then apply it on D. And this is your generalized inverse, right? Okay? Is this clear? This model vector is AB, which is M. So this is your D, this is your G, and that's your M. Okay? All clear? So you have to then compute this to get the inverse. Now, I told you that this matrix may not be invertible. Well, first of all, how did we get this solution? We got this solution by minimizing this error, right? D minus, or D observed minus GM transpose D observed minus GM. Okay? And we took here, we calculated del E del M, and that set that equal to 0, and that gave us the least square solution. Okay? So what if we actually do this? We say that I have this E, which is D observed minus GM transpose D observed minus GM plus some constraints, okay? And let's say this constraint is my, I call that alpha squared times M transpose M. This M transpose M measures the length of the model, okay? And we're saying that I want my model to be small, okay? So if you do this del E del M and set that equal to 0, what you will get is a new solution. M estimated will be your GT G plus alpha squared times an identity matrix D. Okay? Now this, all that this is doing is it's adding a small number alpha squared to the diagonal part of the GTG matrix. And this is called damped least squares. Okay? And this way you can put in a constraint that your model is small. But what this does is that it actually stabilizes the matrix inversion, okay, by adding a damping parameter. And this is called a regularization weight or damping parameter. How do you choose those damping parameters? How do you choose the damping parameter? It's typically trial and error, okay? Because if you set alpha square equal to 0, there is no constraint on the model. If alpha square is very high, then you are simply solving for the minimum length of the model but not matching the data. So it has to be a compromise between these two. Okay? Okay. Now what I will do is this. I will add, let's say, another page so I can write something else on this. Okay. And then I would again go here and do this. Please pay attention to this. What we did is we added this E was simply your data error, right? Now I can define a function f which has a data error plus some weight lambda times some model error. Somebody was talking about this earlier. Is that gentleman here? That if I have some answer, right? Who was that? Somebody was telling me that if I have an a priori knowledge of the model. Okay, so how do we impose that? The way we want to impose this is we have our standard data error, which is your D observed minus GM transpose D observed minus GM plus lambda times, I can say, my M minus M prior transpose M minus M prior, right? That is the prior model, something that you believe your model should be. So what is this measuring? This is measuring the difference between your model and your a priori model, okay? and this is the f. So now we want to minimize this f. Okay? So these are the different kinds of norm you can put, different kinds of constraints you can put in. Okay? And in general, you can have a weighted least squares. So what we have done here, essentially, we have a data norm, right, E, D, and I have a model norm, I'm calling it EM. For now, I will not put the lambda, just, okay? Or you can just put in lambda times dm, okay? This is your f, so I don't know why this is not writing. So both ED and EM, I have written this as L2 norm, right? But they don't have to be L2. If you want, you can make this one L1 or that one L1. First of all, let's say that I want an L1 norm of the data, right? So what does that mean? Your L2 norm is error equal to D observed minus D synthetic square then sum, right? Yeah, then was square root. But this is the square and then sum, right? And what is your L1 norm? D observed minus D synthetic I, right? Okay, so how did we compute the least square solution? What did we do? We took the derivative of E with respect to M and then set that equal to 0, right? Can we do the same thing when it's an L1 norm? Let me ask you a simpler question. Let's say that I have a straight line here, right? And if this is x and this is y, this equation is y equal to x, right? What is the derivative of this equation? 1, right? So dy dx is equal to 1, right? Okay, so now I'm going to have this function y equals absolute value of x. Okay, what would that look like? So this part is the same, right? And that part is this, right? And what is the derivative of this function? So this is minus 1 here, plus 1 here, and here you can't define, right? So it's not differentiable at 0. So this is the problem with L1 norm. So what do people do? Like one of you guys was saying, we cheat. Okay? Yeah, seriously, we cheat. So what we do here is we say that, okay, this is L1 everywhere, but I will smooth it here with an L2. Okay? And there are some other methods. So there is something called Huber norm, which is exactly a combination of an L1 and L2 norm. Then we also have iteratively reweighted least squares. And then there is another method called lasso, which I don't have time to go over, but you will find all of these programs. So why am I interested in L1 norm? What did you learn from that figure I showed you yesterday about the straight lines? This morning, actually. What did you learn? The figure that I showed you, fitting of straight lines with different norms. What was the significance of L1 norm? They were all best fit lines, but using different norm. Good. So that means L1 was least sensitive to outliers, right? So if I want to get rid of some outliers, then I should be using L1 norm, right? So I could actually put an L1 norm on the model also if I want to eliminate some of the spurious model parameters. Okay? Okay. Now we will get our hands dirty and try to solve some problem. Okay? You guys have taken the notes, right? So I'm not going to. Okay. So here is a notebook. How many of you are familiar with Python? Raise your hand. Okay. Everybody knows how to program in Python? Some of you, right? So you can download Python. You can download Anaconda on your laptop. And that is a library that gives you a lot of different machine learning algorithms, plus many other applications. If you don't want to download Anaconda, you can go to Google Colab. Okay? So here is a notebook on Google Colab, and I'm going to show you some examples of linear regression. Okay? So what we do is here we import these libraries. This matplotlib that actually does the plotting. Okay? Okay? I will send you these files, and you're going to have to try it at home tonight. I mean, in your hostel or wherever you are staying. Then we have this NumPy library, and this Seaborn library is quite good also. So we'll try a simple linear regression. Okay? So here what we do is we'll try to fit this model y equals ax plus b. Okay? So our model parameters are a and b, and what I will do here is I will generate some data. Okay? So first I will generate some random numbers because I want to make the data noisy. Okay? And this is my 50, I'll generate 50 values of x and y. Okay? And here I have, first of all, these are different values of x, different values of x. I calculate y equals mx plus c. Here, or ax plus b, a is 2 and b is minus 5. And then I'm adding some random perturbation to it. Okay? And then I plot these data points. Okay? So that's my data, and I want to fit a straight line. Okay? In this particular program, you don't have to generate your G matrix, you don't have to write any of that stuff. Simply call a subroutine or call a function, and that does it for you. So from this sklearn, you call this linear regression. Okay? And then all that you are doing is you're calling your model to be a linear regression model. Oh my God. And then model.fit actually fits the model. And then from the fitting, I compute my y values and then I plot those. So that's your data and that's your best fit straight line. Okay? So your subroutine or this function gives you the values of A and B. Using A and B, you calculate your y and then you plot it on top of your data, and that shows you how well you are fitting the data. Okay? So this is very simple, straightforward, using L2 norm, and you got this. Okay? So you also want to print what values of A and B we got, and it gives you 2.02 and 4.99 minus 4.99, and what we had is actually 2 and 5, right? So this is a pretty good answer given the noise in the data. Okay? What about people at the back? Are you guys watching here or watching the rain? Huh? Okay. Now I'll make it difficult. Well, first of all, before we do that, we can also do a linear regression with multiple parameters. Okay? And you can do the fitting and you can see how it fits. So that's pretty simple. But now I'll make it more difficult. So what I will do is I'll generate some data using a cosine function, okay, in the range of 60 degrees and 300 degrees, okay? And then I will add some normal random noise, Gaussian random noise to it, okay? And then I will plot the data. Here is what data looks like. Can you all see it? Now I'm giving you this data to say do a least squares fit. Okay? So what kind of model you want to fit here? Do you want to fit a straight line? Do you want to fit a cubic? Do you want to fit a quadric? Okay, but this is a linear problem. So you have linear models, yes. So this could be any order of polynomial you can try, but you don't know what exactly is the right parameter. What is the right polynomial, right? So we'll try many of these polynomials. Straight line, then a quadratic, a cubic, quadric, and so on, up to say order 15. So here what I'm doing is I'm generating the model for a whole bunch of up to order 15, and then I can apply linear regression with different degree polynomials. Okay? And so what you see here is this. This is your straight line. This is your power 3. This is cubic. I have plotted every other polynomial. I haven't plotted all the polynomials. This is power 6. This is power 9. This is power 12. This is power 15. Right? So what do you notice here? Somebody from the back who's looking outside? What do you see on the board? Oh, there is a screen there, right? What is that telling you? As you change the order of polynomial, what happens to the fit? Huh? What is that microphone? Who wants to speak? Take the microphone. Okay. Okay, so I think you're right that when you order the degree of polynomial, you are fitting the data better, right? That means your data error is decreasing. Okay? Is it good or bad? Huh? Good. Okay. Now we will see if it's good or bad. Okay? So here this shows you the mean square error in the column. Can you see this? So you can see, as several people pointed out, as the order of the polynomial increases, the error goes down, right? And these are the coefficients of different polynomial. So we got it, but we don't know which one is correct. Somebody is telling me that the order 15 is good, right? What if I went to 26th order? Might be even better, right? Better from the perspective of minimum error in the data, right? Now, but don't forget, this has noise, right? So if your error is going down, what does that mean? You are also fitting the error, right? Fitting the noise in the data. So that would mean that the model is not really good, right? So, but we don't know which order to use. So one of the things we can do is this, which I talked about earlier, is that I can put a data misfit, a data error, and a model error. This beta in this case is model, okay? I should change it to B, M. So this is telling you that the coefficients will be small. That means some of those model parameters would be small, right? But we have to give it some value of alpha, right? So what we do here now, and this approach is called ridge regression, okay? So what we do here now, we try different values of alpha, but take the highest order polynomial and then see how the fit changes. If you look at that, this is for alpha equal to 1.1 10 to the power minus 8, 0.0001. This is alpha equals 1 and alpha equals 5 and so on. So big change, right? So by choosing alpha and a high order polynomial, we are sort of getting the effect of a low order polynomial, but not quite the same, right? That is number one observation. The number two, what we do is we actually use lasso regression, where I have an L2 norm of the data and L1 norm of the model. Okay? And here I use lasso routine to do this least squares or the solution. Once I do that, I start to see these effects. So they are different, right? Okay. So here is a clue. What is the difference between putting L2 norm constraint on the model and putting L1 norm constraint on the model? Remember what L1 does to your model? What L1 does? It actually ignores the outliers, right? Okay. So this notebook basically shows you the effect of choosing L2 and L1 norms on the model, okay? And the effect can be changed by using that weight, regularization weight, right? Alpha. Okay, so I just wanted to remind you of that same straight line fit I showed you earlier. And what you noticed is that L1 norm actually is the robust norm. It ignores all the outliers, right? So what happens in this particular case, well, first of all, what we're trying to do here is by the application of that model term, model regularization term, or the model norm term, we are trying to reduce the values of some of those model parameters so that it's a lower order polynomial, right? With L2 norm, it reduces the model values to a very small number, but with L1 norm, it can go very close to 0. So L1 is more effective than L2, okay? So that's why L1, I would choose L1 in here, okay? Okay. Because L1 reduces your those model values close, they may make those very close to 0. You saw that how it ignores the outliers, right? So if you look at the difference, it makes those very, very close to 0, right? L2 does that, but it goes to a very small number, but not as small as L1 does, okay? Yeah.
That means it is possible, like the L2 model. If it is L1 model, our estimated model parameters can be L2 model.
This is the last part of the equation. The estimated model parameters will be
Close to true model. That means it is coming closer to the difference will be 0.
no, you don't know the true model. Okay? So all that I'm saying is that I'm trying to do some constraints on the model to be within some values, some parameters. And some parameters I don't want them to have really large values. And everyone does a better job in doing that compared to L2. I haven't answered that question yet. So, yes.
But if the data is very low, and if we take data now, are we not taking more to the list?
No, you will basically ignore that. That is the idea, right? So, there is some subjective decisions you have to make once you do this, right? How well is this fit? So, one gentleman just mentioned something that is very, very interesting. Now that we have done all of these exercises, okay, how do we choose the right one for your application? I'm very careful, I'm saying for your application. Yes? Sure, sure. On her, yeah.
The process involves a certain number of iterations. Now, my question is, under what basis are we going to stop the iterations apart from minimization of error?
Okay, there is no iteration here. This is one step. This is a linear problem.
Yes, sir. Now, what I meant about the iteration, let me delete the word iteration. Let me use the word steps. There are a big number of steps to be done with that process.
So we have all of these different weights, right?
Yes, sir.
So how do we choose which one is correct? That is the question I'm trying to answer, right?
Okay.
So what we do here is what is known in machine learning as underfitting and overfitting, okay? And let me address this here. Okay. That's a very important observation. Okay, so you can tell I love to write on this. Okay. All right. So we have some data, right, D, and has a whole bunch of samples of the data. As we saw, we have, right? And I'm fitting all kinds of curves to it, and I don't know which one to pick, right? I've tried L1, I've tried L2. So, number one lesson, and number one thing that you have to remember is that you should not, your goal should not be just to minimize the error. Because if you minimize the error to a very, very small number, you are fitting the noise, okay? And what is the effect of that? So after all, why am I trying to get a model? So that I'm able to predict, right? Let's say that there are some places where I don't have observation. I would like to predict the data using that model. And without even collecting new data, I can predict what my observation is going to be, right? So if you overfit the data, it's not going to be able to predict your model correctly. It's not going to be able to predict your unseen data correctly. So let me put it this way. Let's say that I have like, say, 10,000 samples, 10,000 data points, okay? So what I would do is I would keep about 70% of the data in what we call training data, and 30% as test data, okay? And then what we can do is I try to look at my error. In this particular case, and this is your model complexity, and in this case it's the order of polynomial, right? So what we saw, that this could be your 1, 2, all the way up to 15, right? And what we are seeing is that my error actually goes down like this, right? So that's my training error, okay? And then what I do is each time I train with different polynomial order, I also apply it on the test data, okay? And what you see is that the test data also shows you some curve like this, but after some time it fails to predict, okay? So I would actually use a different color for this. So what you see that after some time, your prediction on the test data actually has more error, right? And this is the point where you are overfitting the data, okay? And that's how you can decide on the model complexity. And I'm demonstrating this with a simple linear model, but you will see this, you will have to apply this on any kind of machine learning applications that you want to make use of, okay? Because you don't know what kind of model should be chosen, but you have a freedom to choose any kind of complex model you like. So these are called hyperparameters. And how do you tune those hyperparameters? You look at this training loss and the test loss, and then you determine where is the overfitting coming in, and that's where you want to stop training. Is this clear? If not, ask me, because if you don't understand this, you cannot go anywhere with machine learning. So here our hyperparameters are model parameters like the model complexity and also the regularization weight. Okay? So what I did here is I look at the data. 70% I'm using for training. I'm keeping the rest for testing. So I'm fitting my lines on 70% of the data. So once I get the model, I predict on the other 30%. Okay? And then see what is the error. So what you see is that typically it will have little more error because that is not the data that was used in your finding the model, right? But it follows the same trend to some extent, but after some time it actually goes up in error. And that basically means that if this order of polynomial is when you start to see overfitting, and you should not be doing that. Okay? Fantastic question. How do we decide that? So what we normally do is we look at the statistics of the distribution, and from that distribution we pick 70 and 30%. Okay? So that you have representative members from both training and test data. Okay? And that's very important. And in a problem which I showed you earlier, I would typically take this. So we fit a distribution, and we pick 70% from there and remain 30% for testing. And we can repeat it for different 70 and 30% until we get a robust set of parameters. Okay? Yes? No, this is the we're talking about linear problems, and linear problems have only one well-defined minimum, okay? So I understand what you're saying. Oftentimes, I understand what you're saying. Oftentimes, you get tricked, thinking that if I'm not fitting the data to a very small error, I'm getting stuck in the local minimum. That is not the case. Because you have to be able to fit the data adequately, taking into consideration that there is noise in the data. Okay? If you take that into consideration and if you're not fitting, then it's a question of local and global minimum. But in this particular context, we're talking about the we're talking about the linear problem only. But that discussion will come up for the nonlinear case pretty quickly. Okay? Anything else? Yeah, unfortunately, you have to try different values. There are certain ways you can do that, and the way one way of doing this would be to look at your say GTG matrix, okay, and you can do the singular value decomposition. Do you know what that is? You can do SVD, and that gives you the eigenvalues. And you look at the minimum eigenvalue, and the reason your solution is unstable is because you have some very small eigenvalues, right? So what you want to do is you want to add some small numbers. So if you can look at the amplitude spectrum, eigenvector spectrum or eigenvalue spectrum, take the highest eigenvalue and take a very small percentage of the highest eigenvalue and add it there. And that becomes your regularization weight. And the reason for this is when you do GTG plus alpha square I, you're adding a diagonal term in the GTG matrix, small number in the diagonal term. And in essence, what this does is actually it adds that alpha square value to each eigenvalue of GTG. Okay? Okay, so I'm going to now talk about the assignment. Okay? Where is Soman? You can ask him to come. Do you have Soman's number or something? Can you ask him to come if he's there? Because he needs to help me with sending these to you guys. Anyway, so the problem here is that of a seismic tomography, okay? And this is a linear problem. And what we're doing here is you can think of this as a seismic tomography problem, or you can also think of this as a standard medical tomography problem. Doesn't matter. What we have is this particular model, which is 16 by 16, okay? And in here, I have sources on this side and receivers on this side, okay? And I'm assuming that my ray paths are all straight line, okay? So then I can write this as D equals GM, right? I'm doing a sort of synthetic experiment. I'm not going to the field and doing this. I'm generating some data using this formula, D equals GM, okay? So here I have 256 ray paths and 256 data points, okay? So your G matrix is 256 by 256. Now we can do this. This problem is discretized into 16 by 16, okay? Of 100 meters by 100 meters. So I'm giving you G, I'm giving you D, I'm not giving you M, okay? So I want you to find M using standard D squares and damped least squares. And there is another method, I think, so I don't know if someone talked to you about this. This is called Tikhonov regularization, which essentially gives you a smooth model. If you want to ignore that, that's fine with me too, but do the first two. But the trick here is to find a way of picking the regularization weight, okay? Try different regularization weights. So here we have, I've given you the G matrix, okay? And the total number of model parameters is 256, okay? It's a 16 by 16 model. I have a G matrix, I have a D vector, and the matrix G is 256 by 256, but in the data, I've written it as a column vector. So you have to split it into a matrix before you use it. And then you can simply plot your answer as a 16 by 16 matrix and see what that looks like, okay? I can tell you that if you did a standard least squares, it's not going to give you good results. How do you know which regularization weight is correct? I bet you that you will know. The answer will tell you that it's correct, okay? There are some written alphabets in there. That much hint I can give you, okay? So you take this data and run this model. If you want to put Tikhonov regularization, you can, but I would not insist on that. Simply do the least squares inversion and the weighted least squares inversion, but you have to try different values of regularization weight. So it's very simple. It's a very simple but a very complex problem. Okay? Because the straightforward application of least squares is not going to work. Okay? So I will pass this one on to someone who will send it over to you. You can't relax in your room. You just have to solve this problem. Okay? And tomorrow morning when we meet, I'd like to go over your answers, and I can also show you what the correct answer would be. Okay? And the best answer will get a prize. Okay. So Somen, I can give it to you and you can send this. So I think that's probably it for today, right? So he will send it to you in the next few minutes, okay? So in the meantime, you guys form your teams. Like I said, you can work in teams. How many are here? 50, right? 50 students? 48? 45? 46? So you can have like 5 teams, 9 or 10 in each team. Sometimes too many cooks spoil the food, so if you want to work on it alone, you are free to do so. Okay? All right. So Somen and I will basically work on it. I'll send you my slides also so you can send it to them. Okay? I think some of you will probably have the answer by dinner time. Okay? Okay? All right. The hard part is to basically take the G matrix and arrange it into from a vector to a matrix and then run it. Okay? Don't ask ChatGPT to solve this for you, because it won't work. The ChatGPT won't know what the correct answer is, okay? All right. I'll see you later in the evening, okay? At dinner time maybe, or definitely tomorrow. Somen, I'm going to email you these right now, assuming that I have internet. No, I don't have internet.